In mathematics and statistics, a stationary process or strongly stationary process, is a stochastic process whose joint probability distribution does not change when shifted in time. Consequently, parameters such as the mean and variance, if they are present, also do not change over time and do not follow any trends. Stationarity is used as a tool in time series analysis, where the raw data is often transformed to become stationary. For example, economic data are often seasonal and/or dependent on a non-stationary price level. An important type of non-stationary process that does not include a trend-like behavior is the cyclostationary process. Note that a stationary process is not the same thing as a process with a stationary distribution. Indeed, there are further possibilities for confusion with the use of stationary in the context of stochastic processes. For example, a time-homogeneous Markov chain is sometimes said to have stationary transition probabilities. Besides, all stationary Markov random processes are time-homogeneous. Definition: formally, let be a stochastic process and let represent the cumulative distribution function of the joint distribution of at times. Then, is said to be stationary if, for all, and for all. Since does not affect, is not a function of time. Examples: as an example, white noise is stationary. The sound of a cymbal clashing, if hit only once, is not stationary because the acoustic power of the clash diminishes with time. However, it would be possible to invent a stochastic process describing when the cymbal is hit, such that the overall response would form a stationary process. An example of a discrete time stationary process where the sample space is also discrete is a Bernoulli scheme. Other examples of a discrete time stationary process with continuous sample space include some autoregressive and moving average processes, which are both subsets of the autoregressive moving average model. Models with a non-trivial autoregressive component may be either stationary or non-stationary, depending on the parameter values, and important non-stationary special cases are where unit roots exist in the model. Let Y be any scalar random variable, and define a time series x star, by. Then x star is a stationary time series, for which realizations consist of a series of constant values, with a different constant value for each realization. A law of large numbers does not apply on this case, as the limiting value of an average from a single realization takes the random value determined by Y, rather than taking the expected value of Y. As a further example of a stationary process for which any single realization has an apparently noise-free structure, let Y have a uniform distribution on 0, to I euro and define the time series x star by. Then x star is strictly stationary. Weaker forms of stationarity, weak or wide-sense stationarity. A weaker form of stationarity commonly employed in signal processing is known as weak-sense stationarity, wide-sense stationarity, covariance stationarity, or second-order stationarity. WSS random processes only require that first moment and covariance do not vary with respect to time. Any strictly stationary process which has a mean and a covariance is also WSS. So, a continuous time random process x, t, which is WSS has the following restrictions on its mean function and autocovariance function. The first property implies that the mean function mx, t, must be constant. The second property implies that the covariance function depends only on the difference between and only needs to be indexed by one variable rather than two variables. Thus, instead of writing, the notation is often abbreviated and written as. This also implies that the autocorrelation depends only on, since. The main advantage of wide-sense stationarity is that it places the time series in the context of Hilbert spaces. Let H be the Hilbert space generated by x, t. By the positive definiteness of the autocovariance function, it follows from Bochner's theorem that there exists a positive measure I1/4 on the real line such that H is isomorphic to the Hilbert subspace of L2, I1/4 generated by E2 I euro E3/4 AT. This then gives the following Fourier-type decomposition for continuous time stationary stochastic process, there exists a stochastic process I ⅓ with orthogonal increments such that, for all t, where the integral on the right-hand side is interpreted in a suitable sense. Same result holds for a discrete time stationary process, with the spectral measure now defined on the unit circle. When processing WSS random signals with linear, time invariant filters, it is helpful to think of the correlation function as a linear operator. Since it is a circulant operator, its eigenfunctions are the Fourier complex exponentials. Additionally, since the eigenfunctions of LTI operators are also complex exponentials, LTI processing of WSS random signals is highly tractable. All computations can be performed in the frequency domain. Thus, the WSS assumption is widely employed in signal processing algorithms. Other terminology: the terminology used for types of stationarity other than strict stationarity can be rather mixed. Some examples follow. Priestley uses stationary up to order m if conditions similar to those given here for wide-sense stationarity apply relating to moments up to order m. Thus wide-sense stationarity would be equivalent to stationary to order 2, which is different from the definition of second-order stationarity given here. Hernaka and Kes also use the assumption of stationarity in the context of multiple-point geostatistics, where higher endpoint statistics are assumed to be stationary in the spatial domain. See also, La copyright v process, stationary ergodic process, Wien-Re-Euro-Kinchian theorem, ergodicity, references. Further reading, Enders, Walter. Applied Econometric Time Series. New York, Wiley PPA 53 ISBN A978-0-470-50539-7. External links. Spectral decomposition of a random function.